So thank you very much for attending our talk. We appreciate it's late in the afternoon, so you might not be feeling like you're ready to absorb any further information today. So really appreciate you coming out. And if someone could take some pictures for my mum, that would be great. So like many of you, we all interact with payment technologies every day. And the reason why we're here today to talk to you about that is because we're very specifically interested in learning about the security vulnerabilities associated with payment technologies. So which is why we're here to talk to you about mobile point of sales terminals. So mobile point of sales terminals has seen quite a big growth over the last few years. We've moved from a single vendor dominating the marketplace to many different vendors just over a short period of time. And you can now get hold of a card reader for about £50 or in some cases for free. Typically, the application process takes about 5 minutes, so it's relatively easy to get hold of an account. You can find these devices anywhere. As you might notice, this is the bar in 44Con, so you can see there's an iZettle terminal there, which we'll be talking about shortly. So for this reason, these devices have become incredibly popular because it's so simple to open an account and get hold of the hardware. So here's just some pictures that I've taken, so you can find them in taxis, cafes. That's a gym I've been to. And so for these reasons, they've also become incredibly popular with criminals as well. So like traditional point of sales terminals and like ATMs, they sit at the endpoint of payment infrastructure, which means if you're a criminal, you can use them for things like testing of cards as well as the movement of money. But we weren't the first to investigate mobile point of sales terminals. So in 2014, thank you. In 2014, researchers from MWR Labs, they investigated the Mura shuttle reader. So at the time, this reader was being white labeled and used by a number of vendors, and this practice is still quite common today. In their presentation, they demonstrated a number of vulnerabilities, of which many have overlap with traditional point of sales terminals. Then in 2015, 3 undergraduate university students from the University of Boston presented their findings on the Square magstripe reader. So we found that both of these projects were really fascinating groundwork, but we didn't feel that they dealt with the more contemporary issues associated with this marketplace. The sophistication of these devices has increased incredibly. So at the beginning of this project, we started with just 2 card readers and 2 vendors. And this quickly grew to a large project encompassing 7 card readers, 4 vendors, and 2 geographic locations. Oh, why is that moving? Don't know why. Okay, for some reason our slides are skipping along, so you'll have to bear with us. So we chose to assess the most popular devices in both the US and in Europe. So we chose to look at PayPal, Square, iZettle, and SumUp. Now, some of these vendors operate in both geographic locations, and where possible, we chose to obtain accounts and readers in both locations. This is because there are some fundamental differences between the processes, the applications, the devices, and the accounts, depending on where you obtain these devices. At the beginning of this project, we had a basic idea of the kind of attack vectors that these devices were susceptible to, but we wanted to see how probable this was in practice. Do you know what's happening with this? Okay. Do you want to use it? Can we? Can I get some technical help? Irony, yes. We have some progression of our slides in a way that we're not expecting. Is there a clicker or something here that's going off randomly? Apologize for this small interruption. I was just using... Yeah, yeah. Very strange. So even technical people need technical people to support them sometimes. So even though we had this basic understanding of the different attack vectors that we were looking at, we still came back to this really simple question of how much security can really be embedded in a device or an environment that's essentially available for free. So we chose to assess 5 different areas of the ecosystem. The first is the communication between the phone and the payment server. Next is the communication between the terminal and the phone. We chose to look at the mobile application and associated mobile ecosystem, the hardware and the physical security mechanisms within the hardware, and then something that we'd like to call secondary factors. So this is things which overall affect the risk and security of the environment, such as the kind of checks that happen when you're enrolling with an account. So first, before I progress any further, I'd like to just provide you with a bit of background on how payments work traditionally and how mobile point of sales terminals fit into this structure. So most of us are familiar that when we go into a shop and we pay for goods or services, you'll either hand your card over to the merchant or you'll interact with the terminal directly. So once your card information has been read, this will be sent to the acquiring bank for that merchant. Now, at this point, they don't actually know who your issuing bank is, so they'll ask the card brands, such as Visa and MasterCard, to determine this information. So once your issuer receives this information, if they're happy with everything, you have the necessary funds to complete the transaction, they'll send the answer back along the chain, and you can complete the purchase. Now, if we take a look at what this structure looks like for a mobile point of sales terminal provider, you can see that the key difference is that the merchant no longer has a direct relationship with the acquiring bank. So instead, the mobile point of sales terminal provider acts like a payment aggregator. So what this means is that they will or won't assess risk at the same level as a traditional acquiring bank. And they might also choose to mitigate some of the risk in other ways, for example, contractually. But it's really important to understand that they are themselves also a merchant. So from here things are pretty similar to the previous diagram that I showed you. We'll be focusing on card payments for this talk, just because this is the core functionality of a mobile point of sales terminal. But it's just worth noting that within most of these devices, within the mobile application, there are features to account for different kinds of transactions, for example, cash. So when you go to make a transaction, there are some kind of lists which broadly describe the different payment methods. This is ordered in terms of highest priority to lowest priority, and it corresponds roughly to the level of security for the payment method. Generally speaking, we can understand that certain types of payments are more risky than others. So for example, it's commonly thought of that chip and PIN is considered high in its level of security. And this is basically because there's a high level of assurance that the cardholder was present during the transaction. Whereas something like swiped or magstripe is considered low in its level of security, and this is because the cardholder assurance, the signature can easily be forged, the magnetic stripe can be cloned, and there's no signing of the transaction, so there's no cryptogram in the transaction. Next, it's important to understand, whilst EMV adoption has been incredibly successful, it hasn't been that fast in certain parts of the world. So for example, in the US, we've seen that there's been an incredibly slow adoption of EMV. So what this means is that we can look to Europe, so we can look to the UK, we can look to other countries, and we can see what kind of attack vectors and payment attacks are occurring here, and we can use them as a good indicator of what will happen in the US. If we look at this in a bit more detail, interestingly, EMV adoption for credit cards is quite high, but you can see that less than 50% of all transactions are actually made using chip. This picture is even worse when we consider debit cards. Less than a quarter of all transactions are made using chip. And only in a couple of years, you'll see that mobile point of sales terminals now will start accounting for almost half of all transactions made via a terminal. So this schematic overview represents how these devices communicate with each of the components. So we can see that the terminal communicates via Bluetooth to the phone, which in turn communicates to the payment server via Wi-Fi connection or over network. So now that we have a broad understanding of how payments traditionally work and how mobile point of sales terminals fit into this structure, we can talk about the findings. So we'll be discussing the sending of arbitrary commands. So this allows us to socially engineer a card holder, so we can get them to carry out an additional transaction, or we can get them to carry out a less secure method, for example, swiped. Then we'll talk about how, for some of the readers we looked at, we were able to modify the amount. So what this means is we can present a much lower amount on the terminal and force the cardholder to authorize a much higher value. We'll be discussing how we obtained remote code execution on the Mura M010 reader. So this provides us with full access to the file system. So what this means is that once you have full access to the file system, you can start doing things like intercepting track 2 information before it's encrypted. You can change the pin pad mode from encrypted mode to command mode, which essentially allows you to then capture pin codes in plain text. Then we'll be talking about the physical security mechanisms. And finally, we'll be discussing the secondary factors. So Bluetooth is the main form of communication between the device and the phone. So therefore, it's important for us to have, at a high level, an understanding of how this protocol works. So I'm just going to make a brief overview of the protocol. So we can roughly divide Bluetooth into 2 different areas, the host and controller layers. So we have the Bluetooth profiles, which deal with the actual transfer of information. Then we have L2 CAP, which deals with segmentation, reassembly, and quality of service. Then we have the host controller interface, which is commonly used for debugging, but it's really handy if you're carrying out some research and you want to understand the functionality of a device. So this is the lowest layer that we can all directly interact with without specialist equipment. Then we have the link manager protocol, and this deals with pairing, negotiation, and encryption. Baseband is the last layer of framing before we have Bluetooth radio itself. And when we talk about Bluetooth, we're actually talking about 2 distinct protocols. We're all very used to interacting with Bluetooth Low Energy, but Bluetooth Classic is the first version of Bluetooth. So with Bluetooth Classic, it uses Bluetooth profiles to communicate to the device, and all of the devices we looked at which use Bluetooth Classic use RF-COM. So what this does is it simulates a serial port, allows you to send large streams of data between the device and the phone. In contrast, Bluetooth Low Energy has quite a small packet size, and it has a very different structure. So it uses GATT, which defines a hierarchical structure under which you have services and characteristics, and each characteristic has a value and a number of properties such as read, write, and notify. If you want to attack a Bluetooth device, you do need to know what its address is. So the Bluetooth device address is made up of 3 main parts. We have the non-significant address part, which isn't significant for any functions, the upper address part, and the lower address part. Now, the lower address part is unique to each device, and you'll find that present in every frame of communication. The non-significant address part and upper address part is what is known as the organizationally unique identifier. Now, if you're an attacker and you can determine what the ranges of organizationally unique identifiers are for a manufacturer, you can go and find potentially vulnerable devices. So, for example, you could go into a public place like a cafe, and you can determine whether you're looking at a mobile point of sales terminal. There are many different Bluetooth attack vectors, but we're just going to be focusing on 2 for the purposes of this presentation. We'll be talking about eavesdropping or man in the middle. So with man in the middle, what we're trying to do is we're trying to follow the connection between the master and the slave in the network. And the second attack we'll be talking about is the malicious device manipulation. So here we're just a bad guy connecting directly to the device, and we're trying to get it to do some things. Some of those functions might be intended by design, and some of those things won't be. So maybe we can exploit a vulnerability. Man-in-the-middle attacks require that you follow the connection between the master and the slave. So you're trying to collect enough information so that you can decrypt the connection. But this typically requires specialist equipment, and the equipment you require depends on the Bluetooth type. So this is where it can get quite challenging for most of us carrying out research. So for Bluetooth Classic, using an enhanced data rate, which many sophisticated embedded systems will do, you'll need something like this frontline BPA 600, which isn't affordable for any of us in this room, I would say, unless you have the support of a company. For Bluetooth Low Energy, on the other hand, you can use an Ubertooth 1, which is reasonably affordable, or you can use something like the Texas Instruments CC2540 dev kit. But overall, carrying out this kind of attack isn't that easy. If you've ever tried it, you'll know what I'm talking about. It's not very straightforward. Secondly, it's worth considering that in the context of talking about payment terminals, most of the pertinent information is going to be encrypted all the way from the terminal to the payment server. So even if you intercept the information, it's going to be useless. So just a special note on enhanced data rates. I didn't find too much information online when I was carrying out this work, so I thought I would mention it. So how do you know if a device supports enhanced data rates and therefore requires very special equipment to sniff the traffic? Well, the first thing that you can do is you can run a reconnaissance scan against the tool. So you can use something like HCI tool and run this against the specific device that you're looking at, and it's going to return EDR as a listed feature of the device. The second thing you want to do is you want to capture some packets in something like Ubertooth, and then if you import it into Wireshark, you can see that all you're seeing is the headers and there's no data payloads. So these two pieces of information confirm that it's not a viable attack method. So this brings us on to our first finding, which is the sending of arbitrary commands. So if we connect directly to this terminal, what would we be able to do? We might be able to initiate a function, for example, to initiate a payment, or we could display text or turn the device on or off. But it's worth also considering as an attacker, in order to carry out an attack like this, we're going to have to carry out some prerequisite work so that we know what the functions are, we know how to access them. And it's also worth knowing that the pairing process can also introduce some obstacles for you. So what you'll need to do this is you need access to a phone which allows you to enable developer options. You need to enable HCI logging. You'll need access to the mobile application for the device, and of course access to the terminal as well. Then what you want to do is you want to collect a sample of the functions. So the easiest way to do this is just to carry out some transactions with the terminal. Then you could import it into something like Wireshark. So here you can see in this example, we've got a device which is sending from the phone to the terminal, it's sending the message insert or swipe card. So here's another example. So I've inserted my card incorrectly into this terminal, and what it's produced is this message which says, please remove card. So we can actually see two packets responsible for the transmission of this data, and that's because it's using Bluetooth Low Energy. We can also see the services and characteristic UUIDs here, so we'll need this information to send the message that we want to in order to manipulate the device. And we can also see the value underneath it. So if we take this value and we deconstruct it, you can see that it's made up of 5 main parts. So the first part contains a command ID, a counter value, and it also contains the payload size that the device is going to receive. Then we have the message, which is in ASCII. Then we have a trailing part and a checksum, which is in X modem, and an end value. So using this information, what we can do is we can force the cardholder to carry out additional payments, and we can also do things like interrupt the payment process and display different kinds of messages. So let's take a look at what this looks like in practice. So here, initially, the cardholder is going to attempt to make a payment using chip and PIN. And I'm just going to send a message which tells them instead to use a less secure method, so swiped. So keep this in mind as we progress through the presentation, because we'll talk a bit more about swipe transactions and the fundamental issues associated with them. So if we take a look at this next example, it looks a little bit different to the previous example. That's because this device is using Bluetooth Classic to communicate. So here we can see the entire data is just sent in one blob, which makes it a bit easier for us. So if we take a look at this in detail, you can see that it's actually quite similar to the previous example. So the first part, the leading part, contains, again, a command ID, a counter value, and a payload size. Then we have the message, and then we have a checksum, which is actually just an XOR value. So we're going to do something similar. So here, we're going to ask the cardholder to carry out a payment. So the card's been read. But instead, what we're going to do is we're going to send a message to the terminal interrupting the payment process and telling them that the transaction has instead been cancelled, which you can see there. But in a moment, what we're going to see on the screen of the phone is that there's a text message that's received by the cardholder which says that the payment has been confirmed. So the only way that a cardholder would know this has happened is if they've enabled a feature like that on their bank account, which they may not have done. So this possibility, the sending of arbitrary commands, led us onto the possibility of fuzzing for mobile point of sales terminals. So what do I mean by fuzzing? So I mean that we could connect to a vulnerable device. We can then send increasing number of characteristics to the device to potentially identify other kinds of vulnerabilities. For example, if it restarts, we might be able to find some sort of overflow vulnerability. So what we've done to carry this out is we just used an ESP32, which is less than £12. It's really cheap, tiny, has a built-in processor, low power, and it supports dual-band Bluetooth, so both Bluetooth Classic and Bluetooth Low Energy. And if you haven't used one of these, I highly recommend it for loads of different projects. They're fantastic. So what we're going to see in this video is the output on the left-hand side of the ESPs. So we are sending increasing number of characteristics. You can see the little bunny on the terminal. We tried to make a cat, but it wasn't, our ASCII art was not fantastic, so I apologize for that. And then you can see we've hit a certain length, which is 32,000 characters, and it disconnects. So this brings us on to our next finding, which is the sending, which is the amount modification. So we're going to use the information that we've learned in the first section to build upon and talk about how we can modify the amount for certain transaction types.
Yeah, sorry, bunny was mine. Now let's try to actually affect the payment process and understand the payment process itself. So actually, there are many ways to intercept all payment commands. Well, first of all, most of commands are going from a server side to the mobile application first, which means if you will intercept HTTPS via HTTPS main in the middle, you can get this data, and for this purpose you need to bypass SSL pinning in most of cases. But if you have your own phone, it's not a big deal. Second method was already mentioned, is just to enable the HCI login and then get data via Wireshark. Then what you actually can do is you can rebuild an application and enable debugging messages and then get access to them via Android debug bridge, as well as rebuilding and reverse engineering of applications can be useful for the case of searching patterns of other commands, specifications of commands, and things like that. And finally, if you don't have any other options, as also was mentioned, you can use some external devices such as Ubuntu. So here are two examples from two different readers for payment commands. And for both readers, we were using two different channels to gather information and find the correlation. So in first case, we rebuilt an application and we enabled HCI login. And you see the payment command and bytes which are responsible for actual amount which be displayed on reader. So actual amount was 750 and it was encoded in hex, so 02EE. And in second case, we also rebuilt an application and intercepted data via HTTPS main in the middle. And in that case, amount was sent in plain text, so 0100. And as you can see here, so for both cases, just to tamper and substitute any amount on a reader you want, you need just to change these bytes and then recalculate checksum. So what actually will happen if fraudulent merchant will tamper an amount between phone and the reader? So customer will confirm and will see less value for payment when service provider actually will see and approve and withdraw higher value amount. So let's have a look in action. We have 1.23 pence which were sent to the server side, to the payment provider, but customer sees and confirms only £1 transaction. And we don't even need to forge signature because it will be genuine one. So this type of tampered transactions will pass at least for MaxStripe. Why? Well, simply because during MaxStripe transactions, card reader doesn't send to server anything except encrypted track to data. When, for example, for EMV transactions, it will be implemented in a cryptogram amount, currency, and all additional information, and it will be checked, and tampered operation will be declined. But for example, for contactless transactions, there are also certain modes, legacy modes, which allow not to send additional information, and they also can be affected for this type of attack. Last problem is that for service providers, limits for all kinds of transactions are absolutely insane, for like up to £50,000 each, which means that service providers rely on the issuing and acquiring bank in terms of blocking of suspicious transactions. So let's imagine ourselves. We can open a merchant account in less than 5 minutes. Then we can force customer to use less secure form of payment, like swipe instead of chip and pin. Then we are going to show him absolutely random amount on a card reader and on a phone, like £1, for example. Yeah, but in fact, we'll be able to make a transaction for up to $50,000 a time. And the last problem is that these fraudulent transactions for some readers can be made with some significant delays. For example, like 10 minutes after customer has already swiped card and has already left the building. So it's quite useful. What can we recommend? Obviously, for service providers is if you still don't have an option to modify the firmware or modify the specification of communication between reader and the phone, you still can mitigate these risks. First of all, it's very important to control the mobile ecosystem, because otherwise customers can use rooted devices and make reverse engineering and tamper data and substitute any commands they want. For customers, recommendations are much easier. Just do not use MaxStripe. Also, what we found is that sometimes get a full access to mobile point-of-sale terminal is much easier than to do it for traditional terminals. For these purposes, you need to just get a good reverse engineer and find him an encrypted firmware so he can work on something. Let's discuss how firmware updating process works and how basically to get unencrypted firmware. All firmware will be stored on a server side, and depending on different vendors, they can be delivered on the readers in different manner. So some of vendors deliver updates as a set of encrypted commands. Some of them delivered updates as links to encrypted firmware, like in this case. And in this case, you can try to obtain some older firmware by basically just brute forcing numbers. But sometimes you don't even need this. You don't need even to open an account, have a mobile phone, anything. So all you need is just to use Google and find some repositories which will lead you to unencrypted firmware, like in this case, which happened with PayPal. So what actually will be inside of this unencrypted firmware? So first of all, it's a whole set of configuration files which will say what messages should be displayed, what types of operations can be enabled, which means we can modify these config files and disable chip and pin, for example. And second, of course, is a whole set of binary files where you can try actually and find some remote vulnerabilities. So basically what we did, so confirmed remote code execution via Bluetooth during the updating process in Miura reader, and in the end we got root access fully compromised reader in the end, which was pretty good because initially it didn't expect anything like that. Why it is so important to have full access to a mobile point-of-sale terminal? One of my favorite cases when in 2014 in Brazil, it was very unusual type of fraud when hackers used compromised mobile point-of-sale terminal. Maybe they compromised it pretty much the same way as here. And they used it to carry out the fraudulent payments with stolen MaxStripe data. But the problem was that they sent to bank information that transactions were actually chip and pin. The most curious part was that this genuine stolen card actually didn't have chip on board. And that's how basically bank in the end found out that that was just a fraud. Second is that just the first idea is start to collect track2 data before it will be encrypted, because you have access to binary file which is responsible for encryption, as well as to collect unencrypted PIN codes, because in fact, in mobile point-of-sale terminals, PIN pad works pretty much the same way as in ATM's traditional point-of-sale terminals. So it has encrypted mode and plain text mode for entering like amount or any other additional information. And if you will have access to a binary file which is responsible for switching between these two modes, you can manipulate this information and force a customer to enter an encrypted PIN code. And finally, of course, this small piece of device, piece of hardware is very useful for understanding previous researches, to making our own researches and projects. So exactly what we did. Last problem was that you need to keep persistence on a device, because there are two potential problems. First of all is that reader, after each rebooting, check his own integrity, which means you can't potentially change the files permanently. But the problem was that they were checking integrity by using certificates which were stored on a file system. So all you had to do is just to substitute certificates with your own, and that's how we bypassed this check. Second check was on the server side, contained the fact that mobile application had to check also out-of-date firmware on the device and forced to update the firmware if it was out of date. But the problem was that this check was bypassed in a very, very dumb way. So all you had to do is just to drop packet with request or response to a server about firmware, and mobile application like took a couple seconds and came back to you by saying, okay, I'm ready to work. So in this scenario, let's imagine that a fraudulent customer can get access to a mobile point-of-sale terminal for a couple seconds. Then he can switch on the pairing mode, connect his own malicious device, and send the remote exploit. Then he can bypass updating process checks and keep the persistence on the device and start to collect track2 data, for example, encrypted, and send to his own server. So what we will recommend in this case, obviously, it is absolutely important to control and should not allow to use your customers out-of-date firmware on the readers, as well as downgrade the firmware, because it's completely unnecessary. We also found a very interesting practice in the market that one vendor checked potentially infected devices and instances, and if one instance, such as account, mobile phone, or card reader, was connected with other instances, all of them appeared to be potentially infected and blocked. Well, and obviously, as soon as we got remote code execution, we could not resist to put more cats on the internet. Finally, couple words about hardware. Surprisingly, for most of these readers, hardware protection, like anti-tampering mechanisms and so on, were pretty much good for these quite cheap devices. Most of them had anti-tampering foil circuit, have protection against opening, drilling, sometimes even pressure sensors. Last problem is that if you will get access to internals without alerts and anti-tampering mechanisms, all you will see in the end is just a set of proprietary protocols, sometimes no GTAC, which means that without developer certificates and without developers documentation, you hardly will get anything from this.
Okay, so this brings us on to our secondary factors. So all of the vendors we looked at really approach security in quite different ways. So some of them place emphasis on the initial enrollment checks, and some instead chose to place emphasis on carrying out transaction monitoring. As I mentioned at the start, there are some significant differences depending on the geographic location. So we found, generally speaking, that devices and accounts in Europe were far more restrictive than those in the US. And that's because for Square, who operate in both locations, this is a really good use case. They, for example, permit the use of MSD transactions and offline processing in the US, but you can't carry out any of those kind of transactions here. It's also worth noting that the mobile ecosystem isn't very well protected on most of these devices. And the problem with that kind of approach is many vendors consider that this environment's already compromised, but this is the very thing that can allow criminals and security researchers, of course, to reverse the functionality of your device. So it's a good idea to protect the mobile ecosystem. So this table that we compiled represents a broad overview of all the different manufacturers, vendors, geographic locations, and areas of assessment that we looked at. So generally speaking, I would say the marketplace places emphasis on usability and enrollment, but it doesn't take into account that if you have incredibly low barriers for entry, your security should in fact be incredibly high. We spoke to all the vendors that were affected, which was all of them, and around 50% of the readers that we looked at. And I'd say that some of them were cooperative and some of them weren't. But generally speaking, it was a very interesting research process for us, and there's many different areas that we still want to look at. So if anyone in this room is really interested in this topic, please feel free to carry on our work or come talk to us about this project. So during this process, we noticed a really interesting opportunity that these devices provide. So normally when you carry out red teaming, which is when you carry out an assessment of risk for a specific technology, in this case payment technologies, you would need to carry that out during a customer engagement, or if you're fortunate to work in a financial organization, you might have more flexibility to do that kind of thing. But generally speaking, this is going to occur during a project. We noticed that here we have some devices that anyone can basically get hold of. You don't have to have a limited company, for example. It's really easy to sign up with these devices and to get hold of one. So this offers a really unique opportunity for everyone in the security industry to consider. Okay, you can get hold of one of these devices, and if you're interested in payment technologies, you can just use them to understand how payment technologies work. You might have read a lot about payment technologies, but by looking at them, you can say, okay, I understand how this process works. You can also use them to test for existing vulnerabilities that you might know about, or in our case, you can do something like carry out new research. So it's really a unique opportunity that we wanted to show to other people that these devices provide. So what does this mean more broadly for assessing risk? It means that if you're a business that takes card payments, you really shouldn't be taking magstripe transactions in 2018. And we've mentioned the numerous reasons why this protocol is deprecated, but more broadly speaking, if you're a merchant and you accept magstripe transactions, you're actually accepting liability for the full value of the transaction. So instead, you should use chip and PIN. But it also raises the question around many different organizations. So we've seen this huge growth in embedded systems over the last few years, both in the consumer area, and we've been integrating these into our organizations. But we need to consider that many of these vendors have only been around for a few years. A lot of vendors don't actually have a working relationship with the security industry. And if you're buying a product that costs less than £200, it's probably not going to be that secure. Sorry to break it to you. So at the beginning of this project, as I mentioned, we started out with just a couple of readers, and this quickly grew to a really ambitious project. So all of the vendors that we looked at, PayPal, SumUp, iZettle, and Square, we found that all of these vendors were affected by our findings, and over half of the readers that we looked at were vulnerable to some form of attack. So this brings us on to our conclusions, which is a very important section, but may not be the most interesting point in the presentation for some of you in the room. So for manufacturers, we recommend that they control firmware. So it's really important to implement controls around firmware, so encrypting and signing firmware, which it prevents from the modification of firmware. It's important to use a Bluetooth method that visually confirms the pairing of the intended device with the phone. And the reason for this is many different Bluetooth attack vectors actually involve some sort of physical proximity initially to initiate an attack. We also saw really strong evidence of security being embedded into the development process in the physical security mechanisms, but we didn't see this in other areas of these devices. So we would recommend to manufacturers that you consider the whole environment as opposed to just the physical device, if at all possible. And it's also worth noting, so with Bluetooth, the protocol itself doesn't actually support anything like input sanitization or user authentication, so this has to be implemented at the application level. So for vendors, we recommend that you shouldn't support deprecated protocols if at all possible, and you should use very strong preventative monitoring practices. This is because this industry clearly has a problem with fraudulent merchants. So the best way to combat that is really to use things like correlation to identify potentially vulnerable devices and accounts. And of course, you should place more emphasis on enrollment checks. This is just because this is your first point of entry into the environment. So for merchants, we recommend that you should control physical access to devices. As I mentioned, many of these attacks involve some level of proximity initially. It's also important not to use magstripe. So this, again, is a deprecated protocol. And when you're a merchant, you're accepting liability for the value of this transaction. We also recommend that you assess the mobile ecosystem, the mobile point of sale system ecosystem, but this isn't really a viable action for many small businesses, but it would be for businesses that are integrating multiple units. And of course, it's a really good idea to try and choose a vendor that places emphasis on security overall. So this concludes the presentation of our findings. Just want to thank you all for coming to the presentation, especially because it's late in the afternoon and we're holding you from gin o'clock. So thank you very much. If you have any questions, let us know.